there are two main important parts of a three-phase induction motor, which are called as the stator and rotor, where the stator is stationary and it is having a stator winding which is three-phase winding, and the three-phase winding is supplied with a three-phase supply and it producing a rotating magnetic field. Okay, so same way the difference, or we can say that what is the difference between the three-phase induction motor and a synchronous motor is that both the motors have similar, you can say, or same structure of a winding which is used in stator, but the difference is in rotor winding. Okay, so now let's see what exactly the synchronous motor is all about and how it is different from our induction motor and how it is used in a very prominent, applications like generator, or rather we can say alternator, and a constant speed machineries where you required a same speed throughout the different load condition. Now, as the name suggests, this particular synchronous name or synchronous word has a meaning, of the speed which is equivalent to the synchronous speed, and your motor is continuously running at the same speed. So it is equipped with three phase AC supply, having a rotating magnetic field, and the frequency by which the electric supply is given to your, so the synchronous speed is 120 F upon P, and P is nothing but the pole pair. So pole pair we cannot change without changing the overall structure of the motor. But yes, frequency plays a very important role in the working of synchronous motor. So we get the value of synchronous speed, and the rotating magnetic field is also rotates at the synchronous speed. Now, because of the rotating magnetic field, we experience that magnetic field is rotating, revolving, and our rotor circuit, which is excited, or we can say it is given a supply with a DC supply. Okay, now what is a speciality of DC supply? That it has a same polarity. Okay, so same polarity होने की वजह से क्या होगा? The magnetic field which is created will be constant. Okay, magnetic field constant होने की वजह से क्या होगा? There will be no change in the magnetic polarity, and there will be an attraction and repulsion between the stator magnetic field, which is rotating in nature, and the rotor magnetic field, which is constant. यहाँ तक समझ में आया आपको?
Yes, sir.
Okay. Now this particular synchronous motor has an another advantage, you can say, or it has an another you can say effect, like it is providing an excitation based power factor. Now what do you mean by that? So if you increase the amount of excitation given to the motor, the rotor circuit basically, then, or we can also say that if the magnetic field strength of your rotor is increased, then the motor will possess a different power factor. And if we reduce the magnetic field strength of our rotor circuit, then we will be getting a different power factor. So we will be getting a either lagging power factor or a leading power factor. So one thing which we are getting is a mechanical energy output, that is we will be getting a rotation, right? The rotation of a shaft, that is the one output we are receiving. Second output which we are receiving is that we can control the power factor of a circuit where our synchronous motor is being connected. Okay, so now this rotor, where it is simply explained as a bar magnet, or as a we can say a permanent magnet, and then it is connected on the shaft. So as soon as the rotating magnetic field rotates, our this particular magnet is tied up, or we can say it is magnetically locked for different polarity, and then the rotor is trying to match with the, like with the speed of rotating magnetic field. Okay, and this is how a synchronous motor is work in the actual field. After that, we get one problem that synchronous motor is not self-starting. Okay, now why it is not self-starting, that we are going to see. But before that, I want to show you one video where you can understand that how exactly this motor, synchronous motor, is work. Okay, so pay full attention and write down the notes what you understood from this. Okay, so if you are ready, just type ready in the chat box, everyone.
As the name suggests, synchronous motors are capable of running at constant speed irrespective of the load acting on them. They are machines with high efficiency and are mainly used in high-precision applications. The constant speed characteristic is achieved by interaction between a constant and rotating magnetic field. Rotor of synchronous motor produces constant magnetic field, and stator produces revolving magnetic field. The field coil of stator is excited by a three-phase AC supply. This will produce a revolving magnetic field, which rotates at synchronous speed. Rotor is excited by a DC power supply, so it acts like a permanent magnet. Alternatively, rotor can also be made of permanent magnet. Interaction of rotor and RMF is interesting. Assume you are giving an initial rotation to the rotor with same direction of RMF. You can see that opposite poles of RMF and rotor will attract each other, and they will get locked magnetically. This means that rotor will rotate the same speed of RMF, or rotor will rotate at synchronous speed. Synchronous speed can easily be derived as follows. This means that if one has got control over frequency of the electricity, speed of synchronous motor can be very accurately controlled. But if the rotor has got no initial rotation, situation is quite different. North pole of the rotor will obviously get attracted by south pole of RMF and will start to move in the same direction. But since the rotor has got some inertia, this starting speed will be very low. By this time, south pole of RMF will be replaced by a north pole, so it will give repulsive force. As a net effect, rotor won't be able to start, or synchronous motors are not inherently self-starting. To make synchronous motors self-start, a squirrel cage arrangement is cleverly fitted through pole tips. At the starting, rotor field coils are not energized. So with revolving magnetic field, electricity is induced in squirrel cage bars, and rotor starts rotating just like an induction motor. When the rotor has achieved its maximum speed, rotor field coils are energized. So as discussed earlier, poles of rotor gets locked with poles of RMF and will start rotating at synchronous speed. When rotor rotates at synchronous speed, relative motion between squirrel cage and RMF is zero. This means zero current and force on squirrel cage bars. Thus, it will not affect synchronized operation of motor. Synchronous motors will produce constant speed irrespective of motor load only if the load is within the capability of motor. If external torque load is more than torque produced by the motor, it will slip out of synchronism and will come to rest. Low supply voltage and excitation voltage are other reasons of going out of synchronism. It is interesting to note that synchronous motor has got the same constructional features of an alternator. Synchronous motors also helps in improving overall power factor of the system. That's all about working of synchronous motors. Thank you.
So now you have seen the facts visually. So now we will see why this starting torque is not there, because recently you see that we need some external force to rotate the rotor in such a way that it will be having an similar direction to the rotating magnetic field. So when the rotor is at standstill condition, like rotor is not rotating, okay, at a standstill condition, and we are applying the voltage to our winding, then this motor will not start because the magnetic field is already there, it is started. But rotor needs to be magnetically locked with it. And how it will lock, that as per the diagram, or we can see the design diagram, you can say design winding diagram, we will be getting to know that how many north pole are there, how many south pole are there, and accordingly we will be getting the connection, or we can say magnetic locking between the stator magnetic field and rotor magnetic field. Okay, but the rotor magnetic field, or we can say this which is a constant value, rotor magnetic field जो है वो आपका constant value का है, बट आपका जो स्टेटर का रोटेटिंग मैग्नेटिक फील्ड है वो, और रिवॉल्विंग, यू कैन से रिवॉल्विंग मैग्नेटिक फील्ड, इट इज रोटेटिंग एट द स्पीड ऑफ सिंक्रोनस स्पीड, तो उसका स्पीड काफी ज्यादा है विद कंपेयर टू द स्टैंड स्टिल कंडीशन ऑफ रोटर, एंड दैट्स व्हाई व्हेन इट इज अप्लाइड to the stator, it is, we can say, there is a gap, always there is a gap between the rotor magnetic field and stator magnetic field, because it is continuously passing. Okay, then this particular RMF is rushes past to the rotor pole so quickly that rotor is unable to get started. Rotor is not able to get started, and इसके reason है, और वो reason है mechanical reason, क्योंकि rotor is connected to the load, mechanical load, right? So whatever the amount of mechanical load this particular motor has to supply, वो continuously आपके magnetic field के ऊपर effect करेगा, and if it is not having that much strength to have a proper magnetic locking, then there will be a problem. So we'll see another demonstration about how this particular synchronous motor is connected and used in various applications. Okay, so if it is attracted first in one direction, then in the other, so there is no starting torque, because there is a continuous north and south poles. Okay, so now you can take a screenshot of this diagram, but you need to draw this diagram in your notebook. Okay, so it will take your 2 minutes to draw this, or 3 minutes to draw this. So just draw this diagram and type done in the chat box when you done. Done, everyone?
What kind of motor is used in this French intercity? Have you ever asked yourself what kind of motor is used in this French intercity train? Well, this train has a 3-phase synchronous motor. As the name indicates, this 3-phase motor runs at constant speed independent of the load. You can get this high-efficient motor in different sizes, and its appliances are varied. The basis of this motor forms the rotating magnetic field, which is produced within the stator by this power supply. The so-called RMF was already explained in another video, so let us have a closer look at the rotor. The rotor consists of constant magnetic poles, which can exist of permanent magnets or be excited by a DC power supply like shown. Assume the rotor has initial rotation in the same direction as the RMF. The A-positive poles of the RMF and the rotor attract each other and get locked magnetically. But if you start this motor at standstill directly, the inertia of the rotor avoids that the rotor can get locked to the RMF. So how make a synchronous motor self-starting? To make this motor able to self-start, a squirrel cage is fitted within the pole tips. So the RMF induces voltage within the squirrel bars, and the motor starts just like an induction motor. At maximum speed, the rotor field coils are energized. Now the poles of the rotor can interlock with the poles of the RMF. At synchronous speed, the relative motion between squirrel cage and RMF is 0, and therefore you have no induction voltage within the bars of the squirrel cage. That's why it will not affect synchronous operation of the motor. A synchronous motor runs at constant synchronous speed, regardless of the load. As load is applied to the motor, the so-called torque angle increases. Note that there is no change in speed, but if the counter torque is increased beyond the maximum torque of the motor will slip out and stop. Let's discuss some information given by the nameplate. All this data refers to the nominal range. The motor's rated mechanical output power is given in kilowatts. The motor rated speed, or full load RPM, refers to full load. This electrical data is important for the stator windings. Here, you can connect the motor in delta. Note that the power factor at rated operation is 1. If the magnetic field of the rotor is excited by a DC power supply, you have further information to connect the rotor. Talking about its appliance, Synchronous motors are, for example, used in high-performance industrial drives for compressors, blowers, and pumps, where an absolutely constant speed is required. Also, in some instances, you find this motor in drive systems for trains. The French train à grande vitesse, or TGV, are some well-known examples.
Okay, so you got then another information about it, which is similar in nature, but also it will help you to understand with the animations. Okay, so now going for an applications of synchronous motors like constant speed and precise speed. What do you mean by that? That whenever we get a constant value of speed and it should be remain unchanged as per the load variation. Okay, now what do you mean by load variation? Whenever we are connecting a load, say for example, have you ever visited a flour mill? आटा चक्की होता है, वो देखा है आपने कभी? तो उसमें अगर कोई वो ग्रेन्स अगर नहीं डाले हैं पीसने के लिए तो वो नो लोड कंडीशन हो गया, उस पर कोई लोड नहीं है. बट वेन एवर दोज ग्रेन्स आर पुटेड इन दैट आटा चक्की और वो इलेक्ट्रिक मोटर से रन हो रही है, तो वहां पर because of the friction you can say, or because of that mechanical load, the speed is started dropping. और speed अगर drop हो गया तो that is not satisfying the criteria of our synchronous motor, and because of that you must say that here in the applications, like we need a constant speed, precise speed, then we are going to use a synchronous motor. Say for example you have a vaccine or you have some medical solution which needs to be mixed properly, and it should be mixed at a very constant speed. Then you can use this kind of motor in variety of sizes where you can get a same speed throughout the application. Okay, so that is a one criteria. Second criteria is about low power motors are like positioning machines, like your machines used in a robotic arms. Okay, so let's see that apart from the trains also where these machines are used. Okay, so just pay attention.
If the motor is overexcited, the motor starts operating as a leading power factor. This way, you can improve the overall power factor. By the way, the graph drawn between armature current and field current is known as V-curve. Note that this synchronous motor and a three-phase generator are of the same structure. A further appliance is the servo drive for robots. Here, this motor is excited by permanent magnets, but this kind of appliance you get in another video in our Learn channel.
Okay, so now we have seen that in robotics also, or we can say low power motors also used in the positioning machines. Positioning machines का meaning क्या है? The robotic arms or a conveyor belts where the low power requirement is there and a very specific movement is expected. Okay, so moving ahead with this, high power low speed is also one of the criteria for the application. Robot actuators में use होता है, also used in ball mills, watches, record player and turntables. Also we can see low speed applications are like rolling mills, chippers, mixers, pumps, compressors. Okay, so these are the different application of our synchronous machine. Okay, there is also one important information about this synchronous motor is that this motor can be used as a generator also as per the excitation condition, as per the excitation we are providing to the motor. Okay,